Joel, where are you headed? Pre-med, pre-health, other? Okay, have you taken concepts or foundations or goals or neither? What else? All right, that's that. All right, so let's talk about the history of life on Earth. So this is basically a very short history of life on Earth. This clock starts at the beginning of the formation of the Earth, which is 4 or 5 billion years ago. We have the first bits of life a billion years or so later. Time to start getting photosynthesis. Eventually we get oxygen-rich atmosphere. And the key here is, really what I want to show you is that it's only in this last little bit that we even have the dinosaurs and the humans. So we've been around for a long, long time with lots of very slow changes and then accelerating changes more. So it's important to recognize that the geology and the biology of the planet have co-evolved with each other. So there was this big bang, right? The solar system and the planet were formed. The initial atmosphere was very reducing, it's hot, it's toxic, it's nasty. There were lots of asteroids bombarding the Earth. On top of that, we had plate tectonics, glaciation. All of these factors are shaping the physical surface of the Earth, the atmosphere, the hydrosphere, the ocean. At the same time, in the biological realm, we have oxygen being produced and CO2 being taken up. Soils are being developed as a result of biological forces, evolution and radiation. As more species evolve, radiate film images. Then, of course, there are mass extinctions. So there are several events we'll talk about a little bit that have drastically and rapidly reduced diversity on the planet. So, against that backdrop, we want to go all the way back and think about what is life, and then we can think about how it might have evolved in the first place. So, here is one definition. There are a few different definitions, but life is anything with the properties of multiplication, variation, and heredity. In other words, anything that can evolve, plus metabolism. So, living things acquire energy from the outside. They use it to sustain their lives and reproduce themselves. Basically, that means that they are taking energy from their environment, and they are essentially they're eating energy and they're excreting energy. So they're basically energy consumers. For viruses or RNA that's replicating in a test tube or computer simulation, none of these things are life under this definition because they don't have any metabolism of their own. So they have the ability to evolve or to reproduce themselves, but they don't have their own metabolism, their own ability to create, consume energy. Okay, so all of these things had to come together in order to we have worked out pretty well. We figured out how these things could have come about. So, again, to sort of summarize, life requires homeostasis, so the ability to be separate from your environment, control your internal environment relative to your external environment. It requires organization, structural organization, so you have to maintain distinct parts in your organism and the connections between them. Metabolism, you have to be able to consume and use energy effectively. You have to be able to control the chemical reactions that are driving those processes, so you need metabolism. You need to be able to use that metabolism to grow and reproduce, to make more of yourself, have offspring. And you need to be able to respond to your environment. So you have to be able to respond to your environment in order to consume the energy that's out there, and to be able to respond to those conditions. Okay. So, earliest life, at some point, so here we have a little timeline here, billions of years in the past, some 4.5 billion years ago, we had at some point, there were probably lots of things that were lifelike early on. Back here, something started to live. There may have been lots of little branches and offshoots that died out, but somewhere along the line, there is some universal common ancestor. The last, in other words, the most recent universal common ancestor to everything that's alive today. So the major groups, bacteria, archaea, eukaryote, there is somewhere, some ancestor to all of those things. Of course, there's a common ancestor here in this tree, but it's not the most recent universal common ancestor. The last universal common ancestor is this thing that we call Luca. Now, before, so Luca, probably in here somewhere, 3.5, 4 billion years ago. Prior to this, there was a lot of stuff going on. It was basically a toxic soup of stuff. There were lots of stuff floating around, and at some point these came together and created this thing that then took off and radiated into all of this. Some example of possible culprits of these stromatolites. These are these formations that are laid down by these prehistoric bacteria, possibly the last universal common ancestor. So, how old is the universe? Does anyone know? More recent estimates suggest. Anyone else? Going once, going twice? Still thinking about it? We're up to 58 months. Anyone? Okay. Alright, so the current estimates are around 13 billion years. There have been estimates of around 20, but we now think that 13 is looking pretty good.
That was good.
Of course, the Earth itself is around 5 billion years old. So, some 13 million years ago, Big Bang, huge explosion, lots and lots of energy, lots and lots of stars being created, swallowing up each other, spreading out, all sorts of stuff going on. Around 5 billion years ago, we get start to get accretion of materials, forming planets, forming the solar system. Chemical soup following after that. At some point, we have RNA starting to evolve, and then eventually into the first DNA-based life after that. So importantly, we are just recycled star material. There was an initial atmosphere that was basically blown off of the planet from all this bombardment that was happening. Solar system, everything was moving faster, so short days. The origin of life occurred on an atmosphere that had a strongly reducing atmosphere, so very, very little free oxygen, liquid water. There will probably happen somewhere under the ocean where there was energy from the Earth itself. It was probably very hot, high pressure, lots of acid. A really nasty place to be if you were to be there today. So just to compare, we have sea surface temperatures today here, and here we have it in over time, and you can see that 4 billion years ago, temperatures were very, very high. And these are just two different estimates of temperature. So if we go back those 5 billion years, back here, we have this again, we've got time on the x-axis. We have abundance of various things on the y-axis. So that early atmosphere was blown off early on. We had very high levels of CO2 in the atmosphere, which has gone down gradually over time. We've had lots of nasty things like methane slowly being drawn down over time. Importantly, oxygen has been very rare through much of Earth's history. It only started to increase a couple billion years ago. Once plants started to consume all that CO2, so driving down CO2 and increasing oxygen in the atmosphere. So the take-home message here is that the atmosphere has changed dramatically over the past several years. And again, here we have just again CO2 declining over time, oxygen increasing. Oldest rocks 4 or 5 billion years ago. Eukaryotes evolving, and Cambrian explosion happening much more recently. So the earliest initial sources of O2 were these photosynthetic bacteria that were in the oceans. So they were using sunlight, just like today's plants, consuming CO2, breathing out oxygen. The initial burst of all this O2 was consumed by oxidizing iron. Remember, we're really reducing the environment, so before we can get free oxygen in the atmosphere, we've got that O2 is going lots of places by oxidizing iron and copper and things like that. And so, in fact, importantly, a lot of the iron ore that's out there that we use for our industrial processes, a lot of that was created in this earlier time. So by oxidizing iron that was previously available in unreduced or reduced form. And eventually, O2 builds up in the atmosphere. So remember, this is all happening in the oceans, right? So we have photosynthetic bacteria in the ocean. Eventually, enough O2 is produced that we build an atmosphere of oxygen. ozone eventually builds up and starts blocking UV radiation. And then this also allows nitrogen to be available as fertilizer, so we get nitrates and nitrites and things like that, so that nitrogen that's available can become available in the soil. So we talked about this a little bit. I added a couple more slides just to expand on it a little bit. So radiometric dating again. So for really old stuff, we can look at uranium 235 decaying to lead 207. And again, these things all decay at some particular half-life, so that we can quantify how long they've been around. And often these are being laid down in igneous rock, so rock that was molten has erupted on the seafloors, for instance, solidifies, and then we can look at the decay in those kinds of rocks over time. We talked about this just briefly, these mid-ocean ridges, but what I want to show you is that this global map of plates, so this is the Pacific plate here. The brown, these are plate boundaries. Some of them are spreading centers, and some of them are coming in, some of them are coming out. So there's a big spreading center here, here, and here. And so, importantly, as we have these plates that are moving, right? They're moving because they're spreading in places like this, and they're being subducted here or over here. They're moving around the surface of the Earth, right? So while they're moving, we can actually, by looking at magnetized minerals in these things and how they, when the magma cooled, it oriented these minerals. And so because of that, we can figure out where they were on the Earth's surface when they were created and when they cooled. And that might not be where they are now. They moved in the meantime. And at the same time, the Earth has been reversing its polarity over very long time scales. And so when you put those things together, you can start to recreate for a given chunk of ocean floor where that floor was when it was created, and you compare that to where it is now. So you can look at it. Yes?